Nah, ada 3 pilar dari Sain komputasi atau computational science. Itu diantaranya adalah AI, machine learning, dan juga data science. Nah, AI ini ya tentunya mungkin sudah banyak yang mengetahui ya, yaitu teknik untuk membuat mesin atau komputer agar mempunyai kemampuan selayaknya manusia. Kemudian untuk machine learning itu bagian dari AI yang dimana dengan machine learning mesin mampu mempelajari pola dalam data untuk kemudian melakukan prediksi. Kemudian Sain data atau data science itu menjadi pelengkap untuk menggambarkan kesimpulan atau pengetahuan yang ada di dalam data, bisa melalui matematika, statistika, maupun visualisasi. Nah, pada sains komputasi ini kita akan membuat ya sebuah tools ya, yang digunakan untuk menggambarkan fenomena fisikal ya, fenomena alam ya, dalam beberapa hal. Misalkan simulasi, prediksi seperti yang sudah disampaikan pada minggu lalu, beberapa fungsi dari sains komputasi ya. Nah, beberapa hal yang seharusnya sekarang sudah sepatutnya layak dipikirkan adalah untuk memanfaatkan machine learning untuk melakukan itu tadi ya. Untuk untuk tadi gitu. Terus kemudian sains computing itu digunakan ya, atau dapat menganalisa event-event yang lalu ya, dan kemudian bisa memprediksi atau kemudian memperkirakan atau melihat kemungkinan-kemungkinan ke depannya. Dengan memanfaatkan sains komputasi itu mesin mampu untuk mengeksplorasi beberapa efek ya dari beberapa skenario ya, dari eksperimen sebenarnya, dan dapat digunakan sebagai sarana untuk pembelajaran. Jadi tidak hanya simulasi saja, tapi beyond simulation ya. Dengan simulasi terus kemudian menangkap pola lebih lanjut, nanti dia bisa memperkirakan atau memprediksi pola selanjutnya. Nah, di sini semakin dibutuhkan machine learning yang dikatakan sini largely missing from machine learning today, yang dimana kebanyakan ya belum dimanfaatkan secara penuh machine learning itu dalam sains komputasi. Oke. Nah, seperti itu. Tapi kita nanti akan membahas atau kita akan melihat ya, mungkin kita melihat video-video saja, video YouTube yang itu merupakan gambaran ya, beberapa research atau project yang telah dilakukan oleh beberapa peneliti yang lain berkenaan dengan simulasi. Oke, jadi pada materi pertama ini kita akan membahas tentang simulasi fenomena alam. Nah, simulasi fenomena alam itu juga menjadi salah satu bagian dari manfaat sains komputasi. Untuk simulasi, itu bisa tadi ya, berdasarkan formulasi teorema dan juga berdasarkan pembelajaran. Berdasarkan formulasi teorema, berarti kita sudah mempunyai persamaan-persamaan matematis yang itu kemudian diterapkan ya, ke dalam code untuk kemudian dilakukan entah simulasi ataukah dilakukan prediksi ataukah visualisasi berupa grafik dan lain sebagainya. Contohnya yaitu teori fluid, teori gravitasi Newton, fraktal dan lain sebagainya. Kan ada tuh apa, mensimulasikan fraktal, mensimulasikan apa, arus laut, gitu. Mensimulasikan gravitasi bumi. Nah, bagaimana benda jatuh terus kemudian disimulasikan dengan komputer grafik. Nah, seiring berkembangnya machine learning, maka semua itu tadi di-generate oleh pembelajaran. Nah, seperti poin yang kedua ini. Ya. Akhirnya menjadi satu topik riset yang menarik lagi, di mana dengan memanfaatkan neural network atau machine learning untuk menangkap pola dari fenomena-fenomena alam. Entah nanti melakukan simulasi, prediksi, dan lain sebagainya. Seperti itu. Banyak hal bisa dilakukan, tapi dalam hal ini kita coba melihat contoh-contoh yang berupa prediksi. Sekarang kita lihat video-video tentang mathematical formulation based simulations.
Dear fellow scholars, this is 2-minute papers with Dr. Karo Jonai Fahir. Today is going to be all about turbulence. We are going to do this, and we are going to do this, and this, and this. To understand what this new paper has to offer, we have to look at an earlier work named Wavelet Turbulence. Apart from the fact that, in my opinion, it is one of the best papers ever written, it could do one thing extremely well. In goes a coarse, low-resolution smoke or fluid simulation, and out comes a proper simulation with a lot more details. And it is typically accurate enough to fool us. And all this was possible in 2008. Kind of boggles the mind, so much so that this work even won a technical Oscar award. Please remember this accuracy statement, as it will matter a great deal. Once again, it is accurate enough to fool us. Now, more than a decade later, here we are. This new paper is leaps and bounds better and can do 5 amazing things that the previous methods couldn't do. 1. It can do spatiotemporal upsampling. Upsampling both in space and in time. What does this mean? It means that in goes a choppy, low-resolution simulation and out comes a smooth, detailed simulation. Wow! Now that is incredible. It is really able to fill in the information not only in space, but in time too. So good. Now, 2. Previous methods typically try to take this coarse input simulation and add something to it. But not this new one. No. This new method creates a fundamentally new simulation from it. Just look here, it didn't just add a few more details to the input simulation. This is a completely new work. That is quite a difference. 3. I mentioned that wavelet turbulence was accurate enough to fool us. So, I wonder how accurate this new method is. Well, that's what we are here for, so let's see together. Here comes the choppy input simulation, and here is an upsampling technique from a bit more than a year ago. Well, better, yes, but the output is not smooth. I would characterize it more as less choppy. And let's see the new method. Can it do any better? My goodness, look at that. That is a smooth and creamy animation with tons of details. Now, let's pop the question, how does it compare to the reference simulation, reality, if you will? What? I cannot believe my eyes. I can't tell the difference at all. So, this new technique is not just accurate enough to fool the human eye, this is accurate enough to stand up to the real high-resolution simulation. And all this improvement in just 1 year. What a time to be alive! But, wait a second, does this even make sense? If we have the real reference simulation here, why do we need the upsampling technique? Why not just use the reference? Well, it makes sense. The plan is that we only need to compute the cheap coarse simulation, upsample it quickly, and hope that it is as good as the reference simulation, which takes a great deal longer. Well, okay, but how much longer? Now, hold on to your papers and let's see the results. And yes, this is about 5 to 8 times faster than creating the high-resolution simulation we compared to, which is absolutely amazing, especially that it was created with a modern, blazing fast reference simulator that runs on your graphics card. But wait, remember, I promised you 5 advantages, not 3. So, what are the remaining 2? Well, 4, it can perform compression, meaning that the output simulation will take up 600 times less data on our disk. That is insanity. So, how much worse is the simulation stored this way? My goodness, look at that. It looks nearly the same as the original one. Wow! And we are still not done yet, not even close. 5. It also works on super high Reynolds numbers. If we have some of the more difficult cases where there is tons of turbulence, it still works really well. This typically gives a lot of trouble to previous techniques. Now, one more important thing, views are of course not everything. However, I couldn't not notice that this work was only seen by 127 people. Yes, I am not kidding, 127 people. This is why I am worried that if we don't talk about it here on 2-minute papers, almost no one will talk about it. And these works are so good, people have to know. Thank you very much for watching this, and let's spread the word together. Perceptilabs is
Oke, baik. Tadi suaranya kedengaran dengan jelas?
Jelas, Pak.
Oke, kita lanjutkan berikutnya.
Dear fellow scholars, this is 2-minute papers with Dr. Károly Zsolnai Fehér. Through the power of computer graphics research works, today it is possible to simulate honey coiling, water flow with debris, or to even get a neural network to look at these simulations and learn how to continue them. Now, if we look under the hood, we see that not all, but many of these simulations contain particles. And our task is to simulate the pressure, velocity, and other physical quantities for these particles and create a surface where we can watch the evolution of their movement. Once again, the simulations are typically based on particles. But not this new technique. Look, it takes a coarse simulation. Well, this one is not too exciting. So, why are we looking at this? Well, look. Whoa! The new method can add these crispy, high-frequency details to it. And the result is an absolutely beautiful simulation. And it does not use millions and millions of particles to get this done. In fact, it does not use any particles at all. Instead, it uses wave curves. These are curve-shaped wave packets that can enrich a coarse simulation and improve it a great deal to create a really detailed, crisp output. And it gets even better because these wave curves can be applied as a simple post-processing step. What this means is that the workflow that you saw here really works like that. When we have a coarse simulation that is already done, and we are not happy with it, with many other existing methods, it is time to simulate the whole thing again from scratch, but not here. With this one, we can just add all this detail to an already existing simulation. Wow, loving it. Note that the surface of the fluid is made opaque so that we can get a better view of the waves. Of course, the final simulation that we get for production use are transparent, like the one you see here. Now, another interesting detail is that the execution time is linear with respect to the curve points. So, what does that mean? Well, let's have a look together. In the first scenario, we get a low-quality underlying simulation and we add 100,000 wave curves. This takes approximately 10 seconds and looks like this. This already greatly enhanced the quality of the results, but we can decide to add more. So, first case, 100k wave curves in 10-ish seconds. Now comes the linear part. If we decide that we are yearning for a little more, we can run 200k wave curves, and the execution time will be 20-ish seconds. It looks like this. Better, we are getting there, and for 400k wave curves, 40 seconds, and for 800k curves, yes, you guessed it right, 80 seconds. Double the number of curves, double the execution time. And this is what the linear scaling part means. Now, of course, not even this technique is perfect. The post-processing nature of the method means that it can enrich the underlying simulation a great deal, but it cannot add changes that are too intrusive to it. It can only add small waves relative to the size of the fluid domain. But even with these, the value proposition of this paper is just out of this world. So, from now on, if we have a relatively poor quality fluid simulation that we abandoned years ago, we don't need to despair. What we need is to harness the power of wave curves. This episode has been supported by weights and biases. In this post,
Oke, berikutnya.
Dear fellow scholars, this is 2-minute papers with Dr. Károly Zsolnai Fehér. Yes, you see it correctly, this is a paper on paper. The paper, if you will. And today you will witness some amazing works in the domain of computer graphics and physics simulations. There is so much progress in this area. For instance, we can simulate honey coiling, baking and melting, bouncy jelly, and many related phenomena. And none of these techniques use any machine learning. These are all good, old-fashioned, handcrafted algorithms. And using these, we can simulate stretching and compression to the point that muscle movement simulations are possible. When attaching muscles to bones, as we move the character, the muscles move and contract accurately. What's more, this work can even perform muscle growth simulations. So, are we done here? Did these ingenious computer graphics researchers max out physics simulation where there is nothing else to do? Oh no, of course not. Look, this footage is from an earlier computer graphics paper that simulates viscosity and melting fluids, and what I would like you to look at here is not what it does, but what it doesn't do. It starts melting these armadillos beautifully. However, there is something that it doesn't do, which is mixing. The materials start separate and remain separate. Can we improve upon that somehow? Well, this new paper promises that and so much more that it truly makes my head spin. For instance, it can simulate hyperelastic, elastoplastic, viscous, fracturing and multiphase coupling behaviors, and most importantly, all of these can be simulated within the same framework. Not one paper for each behavior, one paper that can do all of these. That is absolutely insane. So, what does all that mean? Well, I say let's see them all right now through 5 super fun experiments. Experiment number 1. Wet papers. As you see, this technique handles the ball of water. Okay, we've seen that before, and what else? Well, it handles the paper too. Okay, that's getting better, but hold on to your papers and look. It also handles the water's interaction with the paper. Now we're talking. And careful with holding on to that paper, because if you do it correctly, this might happen. As you see, the arguments contained within this paper really hold water. Experiment number 2. Fracturing. As you know, most computer graphics papers on physics simulation contain creative simulations to destroying armadillos in the most spectacular fashion. This work is of course no different. Yum! Experiment number 3. Dissolution. Here we take a glass of water, add some starch powder, it starts piling up, and then slowly starts to dissolve. And note that the water itself also becomes stickier during the process. Number 4. Dipping. We first take a piece of biscuit and dip it into the water. Note that the coupling works correctly here. In other words, the water now moves, but what is even better is that the biscuit started absorbing some of that water. And now, when we rip it apart, oh yes, excellent. And as a light transport researcher by trade, I love watching the shape of biscuits distorted here due to the refraction of the water. This is a beautiful demonstration of that phenomenon. And number 5, the dog. What kind of dog, you ask? Well, this virtual dog gets a big splash of water, starts shaking it off, and manages to get rid of most of it. But only most of it. And it can do all of these using one algorithm. Not one per each of these beautiful phenomena, one technique that can perform all of these. That is absolutely amazing. But it does not stop there. It can also simulate snow and it not only does it well, but it does that swiftly. How swiftly? It simulated this a bit faster than 1 frame per second. The starch powder experiment was about 1 minute per frame, and the slowest example was the dog shaking off the ball of water. The main reason for this is that it required near 250,000 particles of water and for hair, and when the algorithm computes these interactions between them, it can only advance the time in very small increments. It has to do this 100,000 times for each second of footage that you see here. Based on how much computation there is to do, that is really, really fast. And don't forget that the first law of paper says that research is a process. Do not look at where we are, look at where we will be 2 more papers down the line. And even now, the generality of this system is truly something to behold. Congratulations to the authors on this amazing paper. What a time to be alive! So, if you wish to read a beautifully written paper today that does not dissolve in your hands, I highly recommend this one.
Nah, kalau dibuka, nah ini seperti ini. Jadi memodelkan laminar flow. Solve the 2D Navier-Stokes equation using finite difference method for single-phase laminar flow and verify results using the benchmark cavity test. Di sini autornya sudah memberikan tulisan yang baik ya, mulai dari introduction, mulai dari fluid flow ya, yang merupakan natural fenomena yang biasa dipakai ya, misalkan dalam simulasi waterfall ataukah kopi gitu kan ya, yang splash gitu ya, terlempar airnya gitu dan lain sebagainya. Nah, di sini mencoba simulasikan dengan menggunakan formulasi yang ada. Nah, seperti ini sudah dipaparkan sini. Kontrol volume, terus kemudian formulasinya, ya, equation of continuity in the fluid mechanics, ya, mekanika fluid, ya. Terus kemudian ada prinsip-prinsip conservation of momentum, ya, yang nanti akan menghasilkan persamaan Navier-Stokes ini, yang pada intinya adalah hukum persamaan matematika yang mengatur yang bisa untuk mensimulasikan pergerakan dari fluid itu, dinamika fluid. Nah, ini ada numerical metodenya juga. Terus kemudian ada juga contoh pemrogramannya dengan menggunakan Python. Nanti teman-teman bisa mencoba ya. Dan tahap-tahapnya itu juga sudah dipaparkan di sini, velocities dan lain sebagainya. Ya, seperti itu. Nah, intinya adalah perubahan posisi fluid dari waktu ke waktu. Ini ada contohnya, hasil animasinya, terus bisa menampilkan benchmark block-nya. Ya. Bagaimana fluid itu berubah dari satu waktu ke waktu yang lain. Jadi nanti dicoba ya, kemudian nanti ditulis reportnya, bagaimana hasil cobanya itu. Dan kalau ditulis ya harus dipahami, jangan asal di Google Translate. Jadi kalau ketahuan biasanya kalau langsung Translate tanpa dibaca dulu, tulisannya biasanya nggak nyambung dan nggak enak dibaca. Berbeda kalau misalkan kita sudah membaca, memaham dulu, terus kemudian meskipun menggunakan Translate pada awalnya, pasti kita akan membenahi dan memodifikasi sehingga tulisan itu enak dibaca, lebih tahu maksudnya. Jadi kalau misalkan hanya ketahuan nanti hanya Translate gitu aja, nanti tidak akan saya koreksi ya. Jadi saya akan mengkoreksi. Jadi saya akan spend waktu saya juga untuk mengkoreksi dan membaca untuk tulisan yang niat juga. Kalau tidak niat ya saya tidak mau buat apa gitu. Jadi buat sebaik mungkin, sejelas mungkin hasil percobaan yang sudah dilakukan. Oke, ada pertanyaan di sini untuk yang tugas 1? Oke, kalau tidak ada, sudah jelas ya. Kalau ada pertanyaan silahkan kirim email ke saya, kudistira@ubhj.id. Oke, kita lanjutkan. Sekarang adalah learning based simulation, yaitu simulasi berdasarkan pembelajaran, yaitu memanfaatkan algoritma kecerdasan buatan. Utamanya yang dipakai dalam simulasi yang memanfaatkan learning ini atau pembelajaran itu menggunakan neural network. Seiring dengan sekarang deep neural network, maka peneliti banyak memakai itu ya, karena semakin bisa capture pola-pola yang ada dalam fenomena-fenomena alam. Jadi neural network itu seperti yang mungkin teman-teman sudah pernah mempelajari. Bentuk sederhananya berupa perseptron. Ya kalau diformulasikan matematikanya ya seperti ini. Jadi ada fungsi masuk ke dalam fungsi, masuk ke dalam fungsi, gitu. Seperti itu. Ya kalau digambarkan dalam matematika seperti itu, karena prosesnya kan demikian. Prosesnya kan demikian. Mulai dari dari input ke outputnya kan berjenjang seperti itu. Nah, dalam sebuah neural network itu biasanya ada fungsi aktivasi. Fungsi aktivasi ini yang membuat satu input tadi menjadi non-linear ya, menunjukkan sifat non-linearitas ya. Seperti ini kalau bisa digambarkan pokok-pokoknya ya dalam kerangka dua dimensi seperti ini. Tiga dimensi seperti ini ya. Nah, itu bisa kita lihat bahwa hasilnya itu berupa bentuk-bentuk ya, bobot dan output ya, itu bisa seperti ini. Dan ini yang dinamakan dengan nonlinearity. Jadi menangkap pola-pola yang sebelumnya tidak pernah diduga ya pada persamaan linear. Ya. Kalau persamaan linear ya flat gini aja, ini persamaan linear. Nah, dengan nonlinearity ini bisa mengcapture pola-pola yang kaya. Nah, ini pada penggambaran yang sederhana ya. Ini dari multi-layer feed-forward networks universal approximators. Universal approximators maksudnya universal ya. Universe alam ya. Jadi neural network digunakan untuk mengestimasi atau bisa aproksimasi ya, fenomena-fenomena alam. Nah, seperti itu. Nah, pada perkembangannya, ya, neural networks itu menjadi satu pilihan ya untuk tadi itu ya melakukan learning pembelajaran fenomena itu tadi. Nah, pada semakin kesininya neural network itu semakin dalam dan semakin banyak parameternya pada perkembangannya yang disebut dengan deep learning. Mulai tahun sebenarnya sudah mulai tahun 2012 sampai 2016 ini benchmark arsitektur yang namanya ResNet. Yang ini adalah convolutional base, yaitu merupakan arsitektur yang berbasiskan konvolusi atau convolutional neural network yang biru-biru ini. Ya. Terus kemudian berikutnya transformers pada tahun 2018 dan dia terus berkembang ya sampai sekarang. Jadi ada tendensi bahwa convolutional base arsitektur seperti CNN itu mulai ditinggalkan dan menuju menggunakan transformers. Meskipun riset tentang penggunaan CNN ini masih dilakukan, tapi ternyata transformers menghasilkan kapabilitas yang lebih baik daripada CNN. Nah, dari sini jumlah parameternya tidak terlalu banyak tambah, tapi sekarang tendensinya menaikkan banyak parameter ya, atau banyak neuron yang ada di lampu selektif itu secara apa namanya, gradual ya, terus menaik itu sampai megatron dan seterusnya. Nah, tentunya diperlukan memori yang semakin tinggi juga. Nah, itu ya. Jadi ini yang dinamakan dengan over parameterized model. Bahkan extremely over parameterized model, di mana jumlah parameternya itu sangat banyak, bahkan bisa dalam skala triliunan itu. Nah, itu dinamakan dengan over parameterized model. By incorporating domain specific invariances, we can significantly improve the generalization properties of the neural networks. By incorporating domain specific invariance, we can significantly improve generalizations. Apa yang dimaksud ini? Invariance itu network atau ini ya, NN itu tidak terpengaruh dengan dia itu entah berada di posisi objeknya itu berada di posisi yang berbeda, ataukah objeknya itu posisi yang berbeda, rotasi yang berbeda, skala yang berbeda. Nah, kalau translational invariance ini objek, misalkan gambar anjing ini, itu kan kadang muncul di pojok dari citra, atau misalkan dia sering muncul di tengah-tengah dari citra. Nah, tapi network masih bisa mendeteksi itu dengan keputusan yang sama tanpa dia terpengaruh perbedaan posisi itu tadi. Itu dinamakan dengan translational invariance. Nah, ada juga spatial invariance seperti yang saya katakan tadi. Nah, mungkin dia seperti gini ya, skew ya, layout gitu. Sama, dia masih mendetek itu adalah citra anjing. Tidak terpengaruh oleh variasi-variasi seperti itu, namanya invariance. CNN mempunyai kapabilitas itu. Nah, di sini. Convolutional itu mempunyai kapabilitas itu. Nah, memang invariance itu mendukung atau berkontribusi terhadap hasil klasifikasi, sehingga klasifikasi errornya itu semakin rendah dengan dataset yang sama ya. One reason CNN has been so successful in vision is the translational invariance that is incorporated in them by design, itu tadi. Jadi mungkin bisa dilihat pada di YouTube saya itu tentang convolutional neural network. Kalau ingin mempelajari secara lebih detail teknisnya bagaimana CNN itu bekerja. Nah, improving approximation error with invariance. Nah, tadi invariance itu tadi ya bisa dimanfaatkan juga untuk mengcapture pola hukum-hukum fisika gitu. There are many more invariances other than translational invariance ya. Physics-based laws of nature itu seperti conservation of mass, momentum, energi. Ya. Bagaimana invarian pada CNN itu dapat membantu untuk menangkap ini hukum-hukum fisika ini, ya. Seperti momentum, energi, dan conservation of mass. Ya. Oke. This is the common view of how physics can help training. But even in the big data region, incorporating physics can be helpful. Ya. Jadi selain di-feed dengan data, juga bisa memanfaatkan hukum fisika gitu, ya, agar didapatkan keseimbangan. Kalau kita hanya mem-feed data saja yang banyak dengan big data gitu, tanpa ada arah fenomena, misalkan di sini hukum fisika yang seperti bagaimana yang diinginkan, maka tidak akan bisa mensimulasikan dengan baik. Ya. Nah, kalau misalkan terlalu hukum fisika gitu kan ya, maka ya sama saja dengan yang sebelumnya yang tanpa menggunakan learning algorithm itu tadi, yang menggunakan formulasi matematika itu. Nah, dengan perimbangan antara keduanya, maka mungkin akan menjadi satu simulasi yang lebih baik gitu ya. Nah, itu harapannya seperti itu. Ada beberapa skenario yang ini dinamakan dengan physics informed learning machines. Jadi CNN atau neural network yang dia itu belajar dengan data, tapi masih diinformasikan hukum-hukum fisikanya. Nah, ini seperti bagaimana kita lihat. Ya. There are many more invariances other than translational invariance. Ya. Ya, how can this invariance can help? Ya. Jadi ada suatu kondisi apabila dilatih pada data yang lebih banyak dan data yang lebih sedikit. Ya. Apabila dilatih dengan data yang lebih banyak, maka physical invariance can help make model easier to train with less parameter. Dengan data yang lebih banyak akan dapat physical invariance ini itu membantu model untuk lebih mudah berlatih. Apabila kurang datanya, maka physical invariance itu dapat membantu meningkatkan generalization atau meregularisasi training, yaitu untuk mencegah overfitting. Nah, apa itu physical invariance? Nah, the main question is how can we incorporate these invariances into learning? Nah, coba kita lihat ya. Jadi memang nanti teman-teman fundamental neural network itu perlu paham ya. Nah, pada metode 1 ini train on massive amount of data and hope that the NN trains with the good performance or generalization ya. Coba kita menggunakan physics invariance apa? Let's use Burger's equation as an example. Ini contoh hukum dinamika ya. Yang kalau misalkan di sini bisa digambarkan dengan plot dengan visualisasi yang demikian, itu hubungannya ya, perubahan dari waktu ke waktu. Nah, dengan X ini ya di antara min 1 sampai 1. Nah, seperti yang kita sudah tahu ya, untuk melatih pada neural network ya, kita bisa melakukan misalkan inputnya ini ya, inputnya tadi PDE itu, dan outputnya juga sama ya, PDE juga. Hanya saja ini ada copy ini bisa jadi itu adalah prediksi ataukah pada time step berikutnya dan lain sebagainya gitu. Train on massive amount of data and hope that NN trains with a good performance and generalization. Dengan fungsi loss ini adalah seperti ini. Jadi mungkin bisa digunakan mean squared error dan sebagainya. Jadi U prediksi dikurangi U prediksi dikurangi U. Yang nanti ketika NN ini melakukan pelatihan, maka akan semakin kecil nilai L-nya mendekati 0. Dengan kata lain bahwa input dan output akan semakin mirip. Itulah harapan dari trainingnya. Maka kalau kita input dengan banyak sekali data, massive amount of data, maka harapannya bahwa NN itu akan melakukan hanya dengan performa atau generalisasi yang bagus ya. Masalahnya adalah ya, tidak ada jaminan ya bahwa model itu akan mengikuti conservation law, hukum conservation. Ini salah satu hukum fisika ya. May require a lot of training data and obtaining or simulating this data is not always feasible ya. Nah, seperti itu. Jadi bisa jadi oke, ini bisa jadi secara komputasi itu mirip atau secara angka itu mirip, tapi ketika divisualisasikan PDE-nya itu jadi berbeda, tapi secara angka ini tidak berbeda jauh gitu. Secara ini ya errornya nih ya, errornya ini kecil gitu, antara input dengan outputnya. Nah, untuk menghindari itu maka kita membutuhkan itu tadi physical invariance itu. Jadi kita membutuhkan informasi hukum fisika yang seharusnya ada dalam output itu apa gitu. Nah, misalkan itu tadi, nah ini Burgess tadi equation itu tadi ditambahkan ya, dan dia menjadi sebuah loss function karena yang kondisi ideal adalah ketika fungsi Burgessnya itu sama dengan 0. Coincidentally sama juga dengan di sini bahwa fungsi loss pada neural network itu akhirnya kan dia semakin kecil dan semakin menuju ke 0. Limit sama dengan 0. Jadi dia hanya menuju, mungkin tidak akan sampai 0, tapi dia akan semakin kecil menuju 0. Nah, sesuai. Jadi persamaan Burgess ini akan semakin ideal ketika dia itu semakin 0 atau sama dengan 0. Seperti halnya juga kita meminimumkan reconstruction error-nya di sini tadi. Sehingga jumlah dari fungsi loss keseluruhan yaitu reconstruction loss ini ditambah dengan ini physics loss yang kita tadi menggunakan hukum Burgess itu tadi. Dengan ada variabel regularisasi di sini. Ini biasanya selalu variabel yang bernilai kecil, ya, nanti bisanya dicoba secara heuristik nilainya. Ya, biasanya angkanya itu angkanya kecil 0,001 atau 0,001 seperti itu. Nah, hal itu untuk menjaga bahwa output dari neural network itu sesuai dengan hukum fisikanya. Bisa jadi reconstruction error-nya itu memang rendah, cuma hanya saja tapi simulasinya itu tidak benar gitu. Tapi dengan ini ada trade-off ya. Kalau misalkan itu ada trade-off antara data loss function dan physics loss function. Nah, permainannya itu akan seperti itu terus. Nanti kita lihat contohnya yang berikutnya itu dari Washington University.
Hi everyone, I'm Steve Brunton from the University of Washington, and I've been looking forward to making this video for years. Today I'm going to talk about how we can model very complex fluid dynamic systems. Using sparse nonlinear modeling techniques from machine learning. So this is one of my favorite topics, and this is an area of active research in my lab here at UW. And in 2016, we published a paper where we could build sparse nonlinear models from data of systems, and we looked at the simple laminar flow past a cylinder. This was our kind of big example in our 2016 paper. And so in this lecture, I'm going to tell you about what's happened in the last 5 years and some of the big strides we've made in extending this to much more complex fluid dynamic systems. So from one cylinder to this 3-cylinder configuration that has more broadband turbulence. We're looking at electro convection systems. So this is a complex 3-way coupled device. We're looking at cavity flows. Okay, so really interesting, rich dynamics of this cavity flow. All the way up to spheromac fusion reactor simulations. We can build these sparse nonlinear models. Turbulent wake flows with our experimental collaborators in Europe. So very excited to walk you through some of the progress in sparse nonlinear models of fluid dynamics. In all of these cases, we are going to find models like this, x dot equals f of x, where x is a low-dimensional vector that describes the dominant coherent patterns in these flows. So out of the very complex millions or billions of degrees of freedom you would need to simulate these on a computer, we're going to extract the 3 or 4 or 5 most important coherent structures in X. And F is going to be the dynamics that describe how those coherent structures evolve and interact in time. And that's going to be a sparse nonlinear dynamical systems model. So that's what we're going to do today, and I'm going to jump right in. So I want to acknowledge that this has been work with lots of great colleagues, co-authors, collaborators, great students and postdocs on this. So the sparse nonlinear modeling work started out with Nathan Kutz and Josh Proctor, where we developed lots of the mathematical theory and extensions of the algorithm. And then we've extended this to many fluid systems with Bernd Nowak, J.C. Loiseau from Paris Tech, George Regas from Imperial. college. And I want to also acknowledge the Army and the Air Force funded most of this work. So, and all of this was done by our excellent students and postdocs on these projects. Okay, good. So I want to start off, I'm going to start off on my soapbox here. This is kind of my entry point when I talk about machine learning. So many of you have heard this before if you listen in and you've seen some of my talks. There is a need for interpretable and generalizable machine learning methods. So instead of, we know that neural networks are super powerful, but they're kind of opaque, they're black box. So we want machine learning models that are more interpretable and generalizable. And instead of defining these, I'm just going to make enemies if I try to define these things. I'm going to give you an analogy, okay? So in my mind, the quintessential interpretable generalizable model is F equals ma. So it's interpretable because it has three terms, F, M, and A. They have units. I can write down these equations for a particular system of interest and analyze them, and we can discuss what those terms mean. It's interpretable. It's generalizable in the sense that Newton can learn F equals ma from apples falling on Earth, or so the story goes. And that same model is valid when we design space missions to land humans on the moon. Okay? That is a generalizable model. Now, I have no doubt that if I had movies of apples falling, I could train a deep neural network to make another movie of an apple falling, but that would not be useful to land humans on the moon. It wouldn't be generalizable in this way. This is the kind of model that we want in engineering sciences, in fluids especially, because so many of our applications of fluids are safety critical, like flight, and we can't afford to not understand our model, and we can't afford for it not to work in a regime where we didn't expect it to be. And this is not just Newton. This idea of kind of mathematical modeling being as simple as possible but not simpler is one of the cornerstones of mathematical physics. Einstein observed this. This was observed by Aristotle 2,000 years earlier. Occam, Pareto, you name it. Great minds have been adhering to this principle of parsimony or simplicity to get these kinds of models in physics. And so what that means for us today, mathematically, how we're going to use this in fluid dynamics, is we are going to build low-dimensional models in terms of only the few variables that matter, the coherent patterns in the flow. We're going to extract those low-dimensional representations, and we're going to build sparse dynamics models for how those low-dimensional patterns evolve in time together. Okay? And low-dimensional and sparse are the two mathematical ingredients that are going to give us interpretable and generalizable models in fluids. So sparse models on a low-dimensional state vector. So fast forward 300 years, and in the modern era, we see a great analog of this in the chaotic thermal convection problem, the Rayleigh-Benard convection. So this is a very cool fluids problem where you have a hot plate on the bottom and a cold plate on top. This is kind of a model for how the atmosphere convects when the sun hits the planes and the air starts to warm up and cause these large convection cells. And this fluid flow equation is what motivated Lorentz in 1963 to develop the famous Lorentz model. Now I'll point out, I've added the names Fetter and Hamilton. So this is Linda Fetter and Margaret Hamilton. They were his graduate students who helped him run these supercomputer simulations to generate the data he used to build his model. So I think it's important to remember their contribution. That's the Margaret Hamilton of NASA fame. So she went on to do many, many great things. And what Lorentz was able to do was take this very complex fluid flow field and distill it down into these three equations you see on the right. And you'll notice that this has exactly the low-dimensional and sparse nature that we talked about before. So it's low-dimensional in the sense that Lorentz is characterizing the system with three variables, x, y, and z, that describe three spatial modes that you can add up to approximate this flow field. And those modes were posited earlier by Saltzman at Yale. And it's sparse in the sense that on the right-hand side, out of all of the possible things that could be in the dynamics, there's only 7 terms. Okay, so it's sparse. The interactions of x, y, and z are simple, and there's key mechanisms where they interact through sigma y and minus sigma x and things like that. So that's going to be kind of this key theme, is building these low-dimensional sparse models. And we're going to do this in an automated way. So what I'm going to show you today is how we are automating what Lorentz did in 1963 for more complex flows today with machine learning and with data. Okay, so this is the Sparse Identification of Nonlinear Dynamics algorithm, or SINDY. This is the 2016 paper I was talking about with Nathan Kutz and Josh Proctor. And I'm going to walk you through this on the Laurent system. So imagine that we have the Laurent system, and I'm simulating data, but all I have access to is the data. I don't have access to the equations. So I measure x, y, and z in time. So I've got a time series of these measurements. And I compute x dot, y dot, and z dot, their time derivatives. So I don't know the equations, but I do have data. Now, the simplest thing you might think of to do is to build a linear regression model, a best fit model, that tries to fit x dot, y dot, and z dot in terms of a linear model A times x, y, and z. This is exactly what dynamic mode decomposition, or DMD, does. Now, we know that a DMD model, this is a 3x3 linear model with a single fixed point at the origin. There's no way it can capture this rich complexity of the Laurent system with multiple fixed points, unstable periodic orbits, and chaos. So instead, what we do is we augment the right-hand side with more candidate terms in the dynamics. So instead of just linear terms x, y, and z, we add x squared and xy, y squared, yz, all the way up to, in this case, fifth order polynomials z to the fifth. And all of these gray columns, I can actually build those from the data I collected in x, y, and z. And now the trick is we're trying to find the fewest columns. Remember, we want sparse models. The fewest columns of theta that add up to equal x dot, that add up to equal y dot, and that add up to equal z dot. And when you do this, you uncover, it turns out that the fewest columns that add up to equal x dot, y dot, and z dot highlight the original terms that were in the dynamics that actually generated this data. Now, this is nonlinear system ID. We're generating these models directly from our data, even though we've never seen the equations before. So the sparse optimization, if you had asked me 20 years ago if this is possible, I would have said no. This is a brute force combinatorial search. But it turns out that now this is pretty much a commodity algorithm in statistics to find these sparse linear combinations. So there's dozens of algorithms to compute these things and to find these sparse representations if you build your library correctly. Now, I'll point out, in this case, we assumed that we knew the right measurement variables, x, y, and z. And that's a huge assumption that I'll come back to later. OK, good. If you're interested in trying this, we have open source software called PyCindy in Python. And you can download this on the GitHub and read about it in the Journal of Open Source Software. Good. So we don't just have to build ordinary differential equation models. And here we're going to start thinking about fluids again. We can build partial differential equation models. So this is great work by Sam Rudy, who was a PhD student working with Nathan and me, where he collected full spatial temporal flow fields for the fluid flow past a cylinder. And instead of building just an ordinary differential equation problem, he builds a library of partial derivatives and nonlinear products of partial derivatives. And when he applies the same Cindy sparse regression procedure, you essentially find the sparsest model that's consistent with the data are the Navier-Stokes equations here. And you'll notice that these pink terms are the 1 over Reynolds number. They're within 1% of the true value. So pretty remarkable. Just from data, by applying the sparse regression, you learn the Navier-Stokes equations using sparse regression. Now, because the spatial temporal data is so rich, there's so much of it, we can dramatically subsample the data. We can measure at a few random locations in space and time. And even on that sparse subsampled data, we can still identify the same Navier-Stokes dynamics. So this is pretty cool. OK, good. Now, I told you earlier that we assumed that we knew the right coordinates x, y, and z for Lorentz. So there was some really important work by Kathleen Champion. This was also when she was doing her PhD with Nathan and me, where she essentially combined the idea of a deep autoencoder network from machine learning and our sparse Cindy models that I was just showing you. And so the autoencoder learns a coordinate transformation where your dynamics become sparse in the latent variable z. And so this is a simultaneous discovery of coordinates and of sparse dynamics. So really cool work here. And Kathleen actually has a great video lecture on this that I'll link below. So you can read all about this and see her lecture. OK, good. So now I really want to dive into how we're using this in the field of fluid mechanics. OK, so I'm going to go through vignettes of how we're doing sparse nonlinear modeling to get reduced order models of complex fluid flows. So this reduced order modeling paradigm, again, I'm going to walk you through what we started doing in our original 2016 paper and build from there. So this is our simple low Reynolds number flow past a cylinder. This is a canonical example of vortex shedding. And Bernd Nowak and collaborators in this famous 2003 JFM paper told us the right coordinate system, the right low dimensional variables to measure this, this flow in. So the first two proper orthogonal decomposition modes or singular value decomposition modes, and this third shift mode, which is the unstable steady state minus the mean flow. And if you measure the flow past a cylinder in these three coordinates, you can write down a very simple nonlinear quadratic model here in blue that gives rise to the transient and steady state behavior of this system. This is a famous paper, and it was famous because it wrote down such a simple model for this flow using kind of simple arguments. And this dynamical system in blue gives rise to a slow manifold And it's very kind of interpretable, sparse, and low dimensional. And so this is going to be the example we're going to warm up and try Cindy on to get a sparse model. So we are going to measure this system in those same 3 coordinates, and we're going to take x, y, and z and feed those into our Cindy algorithm. And when we do that, we uncover a model that has essentially the same terms as the NOAC model, and it has the same slow manifold. Our identified system has the slow parabolic manifold, and it captures the same transient and steady state dynamics as the original NOAC model. So this is pretty cool. We were really excited when we saw this. Very soon after putting this paper on the archive, I got an email from Jean-Christophe Loiseau. He was at KTH at the time, now he's at Paris Tech. And he had 2 key innovations that really upped our game in modeling fluids with Cindy. So the first observation is that when we do this sparse Cindy regression, we're not taking into account any background knowledge about our flow. But JC knows that incompressible Navier-Stokes equations conserve energy, and he says they conserve energy. We know how they conserve energy through these skew-symmetric quadratic nonlinearities. And so in our sparse regression, you can essentially add constraint equations so that the quadratic terms have to be skew-symmetric. And by doing so, we make it so that our sparse models conserve energy by construction. So that immediately improves the stability and the learning rate of our models. The second thing he did, and this is, I think, really important, is include higher order nonlinearities into the model. So in our original model, we had quadratic nonlinearities because we wanted to match Barrett-Nowak's model, and we knew that the Navier-Stokes equations had quadratic nonlinearities. But when you allow yourself to have higher order terms, cubic, quintic, septic, nonic, so 3rd, 5th, 7th, 9th order terms, you essentially are accounting for very low energy modes that we've truncated or neglected, and how they affect the large energetic modes we are trying to model. So by adding cubic and 5th and 7th order terms to these x and y equations, we essentially account for these higher frequency mode pairs that we have neglected, these low energy but high frequency mode pairs. And so what you get are much more accurate models, and it's in some sense a rudimentary closure model for this very simple laminar flow. So I want to be careful in calling this a closure model because this is not turbulent, but it is kind of closing the truncated scales and how they affect the large energy scales. So let's see how this works on the cylinder flow and on the cavity flow, 2 of my favorite examples. What we see here in the middle column is kind of our benchmark. A delta is a quantity that's essentially a proxy for the drag. So this is a quantity of interest we want to model in the system. And the white curve is the ground truth from a direct numerical simulation. So when we start off the simulation, the drag rises and it goes to some steady state value. And in yellow and in blue, these are the industry standard state-of-the-art POD Galerkin models. We basically take the proper orthogonal decomposition and we Galerkin project the Navier-Stokes equations onto either 3 modes or 7 modes. So we see that these models, and these are the kinds of models Barrett-Nowak was building in that 2003 paper. So we see that these are qualitatively pretty, they capture the right features, but quantitatively they're off. They have the wrong rise time, they overshoot, and they have steady state error. Whereas when we introduce our Cindy models with either cubic nonlinearities or constraints built in, we almost perfectly capture both qualitatively and quantitatively the dynamics. Now, here's a really important point I want to make. Because these Cindy models are sparse, it's literally a sparse differential equation with as few terms as possible, it is interpretable. JC and I can write down this equation and go get a coffee in Paris and manipulate and analyze that equation. And that's exactly what he did. And he wrote down this differential equation from the Cindy model for cylinder flow and showed that the system is essentially a spring mass damper with a nonlinear damping term, or a van der Pol oscillator. And this is to date the simplest and the most accurate model of the cylinder flow that I have seen on record because of sparsity, because of the sparse regression. Okay, good. Now we have extended this to more complex flows like this fluidic pinball that has 3 cylinders and has much more broadband behavior in the wake. And importantly, we don't need the full flow field or someone to tell us what coordinates to measure this system in. We can build our sparse models directly from lift and drag measurements of these 3 cylinders. So those are kind of obvious measurements you would take. You don't need the full wake velocity field measurements. You just need 6 measurements of the lift and drag on each cylinder, and you can build these very, very accurate Cindy models that match the DNS, the direct numerical simulation, very faithfully. So I think this is super cool. This accounts for some of the issues of, Proper orthogonal decomposition often is going to fail if you change the flow velocity, or I change the geometry, or I move the bodies. But building models directly in lift and drag coordinates is really nice because those are intrinsic, and those mean the same thing even when my flow velocity changes, even when my geometry changes. Okay, good. So now we're going to go on to some more complex examples. So I'm going to go back to the chaotic thermal convection Rayleigh-Bernard. And I want to highlight this really cool work by JC that he put out last year in TCFD, where he was analyzing this chaotic thermosiphon. So it's basically a hula hoop, or an annular region that's heated from below and cooled from above. And it creates and sets up this thermal convection cycle that's chaotic, similar to the Rayleigh-Bernard convection. And so what JC was able to do by extracting modes automatically through dynamic mode decomposition and modeling the evolution of those modes in time with SIMD, he was able to show that this chaotic thermosiphon flow is structurally the same as the Laurent 63 model for Rayleigh-Bernard convection, for a completely different geometry. And so this is a really, really cool result, very nice paper, kind of showing that Lorentz is even more general than we thought to these other flows, and that you can automatically model them using these techniques. So that model was not written down for this before JC, and so this is a real new scientific discovery. Very cool. We've been working on other convection problems. So this is work by Yifei Guan and Igor Novosilov. Yifei was a PhD student working with Igor. He's now a postdoc at Rice, and he was working on this great electro convection problem. So electro convection is a little bit more complicated than standard Rayleigh-Bernard because it has a three-way coupling between the fluid flow, the charge density, and the electric field, which sets up these rich kind of chaotic convection patterns. And so what we did here is started trying to apply these automated sparse modeling procedures to get low order models of this chaotic electroconvection. So we collect spatial temporal data in time, in space and time. We extract the key modes, the low dimensional features, the energetic coherent structures that matter using proper orthogonal decomposition. And then we look at how the amplitudes of those POD modes evolve in time. So A1 is the amplitude of the first mode, A2 is the amplitude of the second mode, and so on. And these are how the mode amplitudes evolve with respect to each other in time. And we noticed that this flow has deep, deep symmetries. There is an incredible symmetry when you look at these mode coefficients of how the energy is being transferred through these modes. And so we were able to learn those symmetries, to write them down, and to enforce them in our SIMD model. So this is using that same technique Jean-Christophe Loiseau taught us. We can now add those symmetry constraints directly into our SIMD model, so we get a nonlinear model that it satisfies those symmetries by construction. And we get this sparse model that has the same skeletal kind of structural dynamics. It misses some of the details, but it captures the big features of this flow very nicely using this. And we can get the flow fields by adding up these POD modes in these A1, A2, A3 combination. So let's zoom in a little more and look at these symmetries. So this is the phase portrait of those POD amplitudes. And we can write down these 5 symmetries that we observe in the system. It's invariant to switching the sign of A2 or switching the sign of A3, and so on and so forth. There's these invariants in the data. And so what that means is that when we write down our SIMD library, the library of possible nonlinear terms in the dynamics, a lot of them immediately have to be 0. We've blacked out a lot of these terms that can't be active with these symmetries being observed. And even more than that, there are other conditions, like this sigma 2 has to be the opposite of this sigma 2, and so on and so forth. There are these kind of additional constraints on the SIMD library that have to be true based on these symmetries. And so when we enforce those in our SIMD regression, we can get away with less data because there's less coefficients we're trying to identify, and we get more stable, more accurate models. In this case, again, we get this model here that has the right structure of the data. Now, it doesn't capture every small feature. There are these little loops here we're not capturing. But we get a lot of the features of the data in kind of this chaotic electroconvection. So very promising that you can scale this up to pretty sophisticated systems. Again, we didn't have reduced order models for this when we started. This is a new model. And you can analyze this kind of how Lorentz analyzed the 63 model. So another great example, this is work by Alan Kaptanoglu, who's a PhD student working with me on plasma physics. So he has a 3-dimensional simulation of a spheromac fusion reactor here that is matched to experiments. And he has, from this simulation data of this 3D system, extracted, again, the low dimensional features we care about using POD, and he had to cook up his own dimensional POD since your magnetic field and your velocity field have different units, so we had to make a conversion so they can speak the same language. And then in this coordinate system, you're able to build a sparse nonlinear model that satisfies the constraints of the PD, of the MHD equations. And down here, you see that our reduced order model, our sparse nonlinear model, captures the structural dynamics of this sphere-Mac fusion reactor very, very accurately. So this is very promising. We're starting to add things like injector dynamics and control so that we can use these reduced order models for online control of experiments, hopefully. So that's where this is going, is these models are so fast and so efficient, and they seem to be pretty accurate. Maybe we can use this for something like model predictive control down the road. Okay, good. So I'm just going to keep going because I love this stuff and we've got more. I've been kind of blown away with the progress in the last few years. If you had asked me 2 years ago if some of these flows were possible to analyze with Cindy, I would have said probably not. But with great students and great collaborators, we've started opening up a lot of these problems and complexities. So one of the ones I'm really excited about, this is new work by Jared Callahan, a great PhD student of mine, and JC Loiseau. The archive paper should be coming out very soon, where we're analyzing more complex, higher dimensional systems like this shear-driven cavity that has, if you did the proper orthogonal decomposition, you would find that there might be a couple dozen modes that are energetic and important. And so when they analyze this flow, of course, you have the shear layer instability and you have the inner cavity modes. Like, this is classical theory. We know that these are dominant kind of mode structures that give rise to these dynamics. But in a purely data-driven fashion, again, when we look at the mode amplitudes versus each other in time, so A1 versus A2, A2 versus A3, and so on, you see this incredibly rich correlated structure here that's highly indicative of nonlinear dynamics. And so by identifying the two driving mode pairs, Jared and JC were able to build this extremely simple Cindy model up to 5th order that almost perfectly captures the dynamics of the full nonlinear simulation. And if we zoom in, we can look at the power spectrum of the log of the energy. And we have power peaks from the cavity mode and the shear layer mode. We have power peaks from kind of these harmonics, the second harmonic, the nonlinear crosstalk, and higher order harmonics. And our Cindy model almost perfectly captures all of them. This blew me away when I saw this. Absolute beautiful agreement of many, many modes, all the way up to like A19 in this case. That's the 19th POD mode. So we're capturing the full spectrum of this cavity, again, with a 2-state Cindy model, and then kind of how they impact these higher modes. Very cool. You can read about this soon on the archive. And another thing kind of I'm really excited about that I wouldn't have thought is possible a couple of years ago is extending this to full-blown turbulence systems. So turbulence is hard because you have coherent structures, but they're forced by multi-scale structures that you don't want to model or necessarily kind of keep track of. And so this is work by Jared, JC, and George Regas, where we essentially are modeling the Langevin dynamics of turbulent fluid flows. So here we have x dot equals f of x. That's our original Cindy model for the coherent structures, plus sigma w. This is a noise term, a colored noise term that forces our dynamics stochastically. And so what we're doing here is we're simultaneously identifying the sparse nonlinear dynamics of the coherent structures and the colored noise forcing of all of those small scale turbulence fluctuations that are forcing the system. This is closely related to the Fokker-Planck equation, which describes the evolution of distributions or ensembles of trajectories, but we're taking the Langevin approach. And I'll point out, we're building on prior work by Bonasega and Clementi and others that extended Cindy to Langevin systems for molecular dynamics. So we've extended it to higher dimensional fluid systems. And I'm not going to jump into all of the details here because it's a little bit involved, but the basic idea is that we're parametrizing our nonlinear dynamics and our noise, just like in Cindy. And then we're finding sparse nonlinear models by fitting the data, by essentially building distributions and by adjoint optimization, trying to find sparse Xi vectors that model these nonlinear dynamics and noise forcing. And in all of the cases we've looked at, from simple toy examples to fully turbulent wake data from experiments, we get very simple structural models for the coherent structures and a very simple representation of the colored noise forcing from the subscale turbulent fluctuations that we're not modeling or we're not keeping track of. And just to illustrate this on the cavity flow, this again is the full direct numerical simulation. And down here, this is our Langevin reduced order model. So you can see that we're capturing kind of the key dynamics of these POD modes, these kind of figure 8 dynamics, but we're also getting the spread of the dynamics because we're accounting for this noise forcing that broadens those trajectories. Very, very cool. And it seems to work on this fairly turbulent, sorry, not this, but on really turbulent data like wake data from experiments. Okay, good. So I think the last thing I want to show you, I've shown you a lot. This is a whirlwind tour of sparse nonlinear modeling of fluids. The last thing I want to show you is pretty new, and it's a little bit of a different take on sparse modeling. Again, with Jared Callahan, James Koch, Nathan Kutz, and Bing Brunton. And this is sparse modeling of terms in equations to see which terms balance each other at what locations of space and time. So there's this idea of dominant balance in physics, where even if you have a very complex equation, like the full 3D Navier-Stokes equations, maybe at a location in space, only a few of those terms are active and large and are kind of balancing each other out, while most of the other terms are small. So this is the idea of dominant balance, and it's the foundation of asymptotic analysis and asymptotic expansions. Most of the applied math departments in the country grew up out of this idea of asymptotics and dominant balance in physics, where you could write down solutions on pen and paper by hand before computers by simplifying the equations to a few key terms that are interacting. And what Jared's going to do on this Johns Hopkins turbulent boundary layer is automate this dominant balance procedure with machine learning and sparse nonlinear modeling. So if you take the Reynolds average Navier-Stokes equations, the RANS equations here, you see that there are, in 2 dimensions, there are 6 terms. And for each of those terms, you can essentially plot what that term's magnitude is at every point in space. So this is one term in my equation at every location in space on the boundary layer. And you can plot all 6 of those equation terms like this. So this is essentially an equation space representation. So now for every point, I can take that point and I can plot it in a 6-dimensional equation space in all of these 6 coordinate axes. And that's exactly what Jared did. So this is just 2 slices in equation space of all of those points. And you'll see that the data appears to live on these kind of subspaces or clusters. So Jared applies relatively simple machine learning clustering, in this case Gaussian mixture models, to find which clusters are active, how the data clusters. And I'm only showing you a couple slices, so there's other dimensions where the other terms cluster. And again, dominant balance is about trying to figure out which terms are small, almost 0, and which terms are big and are balancing each other. So what we're going to try to do, for example, this red set of points here, this red cluster, this term is approximately 0, and these 2 terms are in a balance. So we're also going to apply sparse subspace identification, or sparse PCA, to find which terms are active, approximately active, and which terms are approximately 0 for each of these 5 clusters. And so again, these black squares are the terms that are approximately 0. And what's really cool is that every point here, you can replot that point in space, where it was in space, and you find that these 5 regimes of dominant balance correspond to 5 classical regimes from the boundary layer. So we recover the viscous sublayer, the inertial sublayer, the transitional region, purely in an automated data-driven fashion. So this is phenomenal. This allows us to actually uncover these dominant balance regimes purely from data with relatively simple sparse modeling, right? We're trying to find the sparsest combination of terms that are active in these clusters. And again, this recapitulates classic boundary layer theory that was hard fought over the last 100 years by many, many smart people. So we've looked at this for the boundary layer I just showed you. We've looked at this for the super continuum laser, this
Oke, jadi ini adalah salah satu contoh ya penggunaan apa namanya convolutional neural network untuk memodelkan fluid, Nah, tapi yang menarik adalah nah, ini adalah salah satu arsitektur neural network yang neural network itu bisa berupa konvolusional ataukah hanya berupa perseptron, perseptron. Jadi tergantung datanya seperti apa ya. Akan tetapi secara struktur ini itu adalah arsitektur autoencoder namanya, autoencoder. Nah, yang dilakukan oleh Steve Burton ini adalah mencoba untuk mengambil sisi tengahnya ini. Ini yang dinamakan dengan latent space. Latent space itu adalah ruang tersembunyi. Nah, ketika itu tadi beberapa simulasi fluid itu tadi dimasukkan, terus kemudian keluarnya juga simulasi fluid yang sama, ya, simulasi fluid yang sama. Dan network akan terus berlatih secara berulang-ulang. Secara berulang-ulang berlatih. Nah, dari hasil latihannya itu apa? Nah, nanti di tengah-tengah sini ya akan mengenerate beberapa subpola, ya, subpola dari fluida itu, ya, subpola. Nah, nanti subpolanya itu seperti nah, ini adalah contoh ya, subpolanya dari pola-pola bagian dari fluid itu, ya. Jadi seperti yang digambarkan dari awal itu ya, di awal sekali itu ada
Looking forward to making this video for years. Today I'm going to talk
nah,
about
ini pola seperti ini kan nampak chaos gitu kan ya, nampak chaos. Ya mungkin bisa di breakdown gitu kan ya, pola fluidnya itu jadi sub pola yang bagian gitu, nah, yang beraneka ragam ya, dari yang nampak chaos seperti ini. Nah, itu simulasi per bagian-bagian atau sub dari fluidanya itu, sehingga tadi dia mengatakan bahwa pada bagian akhirnya nah ini pada bagian akhirnya ini jadi banyak subpola yang seperti ini di dalam representasi tengah dari autoencodernya. Nanti ketika selesai di training, nah, diekstraksi sub-subpola. Ini bisa masing-masing bisa disimulasikan. Kalau misalkan dalam time and space, ya bisa sub-subpolanya itu disimulasikan. Begitu. Jadi melihat sub-sub bagian dari aliran fluida itu dalam fluida yang besar yang nampak chaos itu tadi. Itu satu hal yang menarik di dalam simulasi fluida dengan menggunakan machine learning atau dengan menggunakan autoencoder tadi. Nah, hal semacam itu sekarang sedang banyak ya, sedang banyak dilakukan ya saat ini. Ini sebelum ke sini itu sama halnya dengan ini, sama halnya dengan sama halnya dengan apa namanya COVID. Itu enggak ya? Sama halnya. Tidak melulu berupa data spatiotemporal itu tadi ya. Ini juga dalam grafik juga, dalam multivariat grafik seperti ini. Misalkan dari beberapa pergerakan, dari beberapa graf, ya, dari beberapa variabel yang sangat banyak ini ada beberapa variabel itu tadi. Terus kemudian outputnya itu sama ya, outputnya ini sama. Nah, kalau dilatih terus nanti yang di tengah-tengah sini nanti akan membentuk faktor-faktor kalau membentuk ini apa namanya yang memicu pergerakan-pergerakan ini tadi, sehingga di tengahnya itu tadi bisa saya visualisasikan seperti demikian ya. Nah, jadi bagian-bagian yang di highlight itu adalah faktor yang membentuk grafik-grafik output itu tadi, sehingga dalam skala big data yang besar, maka ini akan dapat di capture ya, highlight ya, penyebab-penyebabnya. Itulah yang dinamakan dengan latent space itu ya. Jadi ruang tersembunyi yang di tengah di dalam autoencodernya itu tadi. Oke.